In spite of its many successes in the realm of atomic physics, what passed for quantum theory prior to 1925, what we today call the old quantum theory, it was a mess, particularly for systems containing many electrons. It was a hodgepodge of hypotheses, heuristic principles, theorems, and computational recipes with no logical consistency or conceptual autonomy. Every quantum system had to be first solved classically, and then the solution translated into the quantum framework using a combination of skillful guesswork, intuition, and the magic of the correspondence principle, and in a matter that did not carry over straightforwardly from one problem to the next. The correspondence principle, which was championed by Niels Bohr, is based on the realization that quantum theory has to reduce to classical mechanics in the limiting case of h tending to 0. Indeed, as early as 1906, Max Planck had shown that quantum equations converge to the classical results in the limit h tending to 0. In Planck's radiation law, if we expand the exponential in the denominator and neglect higher powers of h in the limit h tending to 0, we see that Planck's radiation law reduces to the Rayleigh-Jeans law. This can also be seen in Einstein's fluctuation formula. As h tends to 0, the first term, which corresponds to the Wien law, vanishes, and we are left with only the second term, which corresponds to the Rayleigh-Jeans law. In June 1922, Niels Bohr was invited to the University of Göttingen and delivered 7 lectures on the theory of atomic structure as part of the Wolf-Scale lecture series. In 1908, the mathematician Paul Wolfscale of Darmstadt had bequeathed 100,000 marks to the Academy of Sciences in Göttingen to be awarded to the first person to publish a complete proof of Fermat's last theorem. Fermat's last theorem, formulated in 1637, states that there are no non-zero integers x, y, z, and n greater than 2, satisfying x to the power n plus y to the power n equals z to the power n. As you know, Fermat's last theorem was finally proved only in 1995 by Andrew Wiles. And meanwhile, skyrocketing inflation in Germany during the Weimar Republic years depreciated the value of the mark and reduced the value of the price to almost nothing. But before that, the Wolf-Scale Committee wisely decided to use the interest on the money to invite prominent scientists as guest speakers to Göttingen. These speakers included Poincaré in 1909, Hendrik Antoon Lorentz in 1910, Arnold Sommerfeld in 1913, Peter Debye in 1914, and finally Niels Bohr in 1922. At these lectures in June 1922, and in the subsequent discussions that followed, Heisenberg criticized Bohr's quantum theoretic formulation of the quadratic Stark effect. Heisenberg was influenced by the philosophy of logical positivism, and he tried to formulate a new kinematics using only observable optical quantities such as the frequencies and intensities or amplitudes. At this point, let me introduce the main actors in our story, or the dramatis personae. The scene of the action is the University of Göttingen, the group of Max Born, professor of theoretical physics, and his assistants Werner Heisenberg, Pascal Jordan, and Wolfgang Pauli. James Franck is the professor of experimental physics, whose spectroscopic results proved crucial in the story. David Hilbert is a professor of mathematics, and his understanding of matrix algebra and concept of infinite dimensional vector spaces proved crucial to the development of quantum mechanics. Then there is Norbert Wiener visiting from MIT. We will also talk next week about Louis de Broglie, who had just submitted his PhD thesis at the University of Paris, and Erwin Schrödinger, at Zurich, and also Paul Dirac at Cambridge. Then there are the peripheral actors whom we have already encountered. Albert Einstein, who carried out a lifelong correspondence with Max Born, and Niels Bohr, who interacted with practically everybody. Expanding such a time-dependent property xn of t in terms of its Fourier components, that is sigma m, x of n and m, e to the power 2 pi I nu of n and m t, Heisenberg found that the Fourier amplitudes x of n and m satisfy these relations, whereas the frequencies satisfy these relations. Now, to represent the quantity xn squared, he then found it necessary to postulate that xn n minus m squared is equal to sigma k xn n minus k into xn minus k n minus m. Generalizing this to two different properties, x and y, he found that they don't commute, that is, xy is not equal to yx, a result that Heisenberg found deeply unsatisfactory. He then applied his formalism to the anharmonic oscillator and the rigid rotor to get the energy expression for the harmonic oscillator E equals n plus half h nu 0, in contrast to the old quantum theory, which only gives E equals n h nu 0. These results were obtained exactly 100 years ago at the end of May 1925, while Heisenberg was recuperating from a bout of hay fever on the island of Heligoland. After returning to Göttingen in June, he wrote up his paper and presented it to Max Born in the middle of July. Born at once recognized its importance and sent it to the Zeitschrift für Physik, where it was received on July 29th and published under Heisenberg's name. The novel aspect of Heisenberg's approach was the representation of physical quantities by sets of time-dependent complex numbers and his strange multiplication rule. As Born recalled many decades later in his Nobel address, Heisenberg's multiplication rule did not give me any rest, and after 8 days of concentrated thinking and testing, I recalled an algebraic theory which I had learnt from my teacher, Professor Rosanes, in Breslau. Thus, it was Max Born who recognized that Heisenberg's sets of complex numbers were actually the matrices that he had learnt as a student at the University of Breslau in 1903, and that Heisenberg's multiplication rule was simply the rule for the multiplication of matrices formulated by Arthur Cayley in 1855. Referring to the sacrifice of the commutative property associated with the introduction of this algebra, Heisenberg later said, "Almost every progress in science has been paid for by a sacrifice. For almost every new intellectual achievement, previous positions and conceptions had to be given up." The first volume of Courant and Hilbert's famous textbook Methods of Mathematical Physics was published at the end of 1924, based on David Hilbert's lecture notes and covering much of the math needed for the subsequent development of quantum mechanics. One of Courant's assistants in this endeavor was Pascual Jordan, who thus became somewhat of an expert on matrix algebra. Soon after the publication of Heisenberg's first paper, Born was looking for a qualified assistant to develop the new quantum mechanics, but there were not many physicists who were familiar with matrix algebra. While traveling by train to Hanover one day, Born was talking to a colleague about his work and mentioned his difficulty in finding a suitable assistant. Jordan happened to be in the same compartment and overheard this conversation. When the train reached Hanover, Jordan introduced himself to Born, described his experience working with matrices, and offered to work with Born on this project. Thus began their fruitful collaboration, leading to their paper on quantum mechanics, which was received at the Zeitschrift für Physik on September 27, 1925. The Born-Jordan paper consists of 4 chapters. The first chapter expounds the theorems of matrix algebra, while the second chapter develops the foundations of quantum mechanics of non-degenerate systems with 1 degree of freedom. Writing the Lagrangian matrix L equals PQ dot minus H, where H is the Hamiltonian matrix, a function of the coordinates Q and the momenta P, we find that the velocities Q dot are given by this expression, and from the expression for the Lagrangian, taking the partial derivative with respect to Q dot, we get P, and taking the partial derivative with respect to Q, we get minus del H by del Q. From Lagrange's equation of motion, that is d dt of del L by del Q dot minus del L by del Q equals 0, since del L by del Q dot is equal to P, we get P dot is equal to del L by del Q. If the Lagrangian has no explicit time dependence, we can write the variations of the Lagrangian as a sum of the variations due to variations in the coordinates q and variations in the velocities q dot, and therefore delta L equals P dot delta Q plus P delta Q dot, since we have already shown that del L by del Q is equal to P dot and del L by del Q dot equal to P. And that can also be written as P dot delta Q plus delta of PQ dot minus Q dot delta P. So for variations in the Hamiltonian, delta H, since H is equal to PQ dot minus L, we can write delta H is equal to delta of PQ dot minus L, which using the previous expression becomes Q dot delta P minus P dot delta Q. But the variations of the Hamiltonian are the sum of the variations due to the momenta P and due to the coordinates Q. So equating the coefficients of delta P and delta Q in these two equations, we get Hamilton's equations. Del H by del P equals Q dot and del H by del Q equals minus P dot. So far this is all classical mechanics, except that H, P and Q are matrices and not just variables. Born then used the expression for quantization of action from the old quantum theory, that is the cyclic integral of P dq is equal to nh, an integral multiple of Planck's constant, and that is equal to the integral of pq dot dt. Performing this integration yields this expression, where we have used the expansion for the coordinate and momenta matrices introduced earlier, and that equation can then be rearranged in this form using the Heisenberg identity introduced earlier, and that can then be expanded out by performing the differentiation, and this equation is just the matrix commutation relation, that is PQ minus QP is equal to H by 2 pi I times the identity matrix I. Okay. As we will see, this commutation relation leads directly to Heisenberg's uncertainty principle. As Born recalled, I shall never forget the thrill I experienced when I succeeded in condensing Heisenberg's ideas and quantum conditions in the mysterious equation PQ minus QP equals H by 2 pi I. The novelty of Born's result was recognized by Heisenberg, who later admitted the fact that xy was not equal to yx was very disagreeable to me. I felt this was the only point of difficulty in the whole scheme, otherwise I would be perfectly happy. I had written down the quantization rule, but I had not realized that this was just PQ minus QP. The third chapter of the Born-Jordan paper applies the theory to the harmonic oscillator and retrieves Heisenberg's result, showing also that the only allowed transitions are between adjacent energy levels. The fourth chapter concludes with a discussion of the quantization of the electromagnetic field. In November 1925, Born, Heisenberg and Jordan submitted a comprehensive exposition of quantum mechanics in its matrix formulation, their famous Drei-Mähler-Arbeit, or three-author collaboration, entitled Zur Quantenmechanik II, or or on quantum mechanics too, also published in the Zeitschrift für Physik. From the matrix commutation relation, any function f which can be expanded in a power series in P and Q will satisfy the equations fq minus qf equals h by 2 pi I times del f by del p, and pf minus fp equals h by 2 pi I times del f by del q, with f being equal to h, and using Hamilton's equations, this gives p dot equals minus 2 pi I by h into ph minus hp, and q dot is equal to minus 2 pi I by h into qh minus hq. Similarly, from these equations, we can show that for any function f which can be expanded in a power series in P and Q, its time derivative will be given by f dot is equal to minus 2 pi I by h into fh minus hf. Taking f is equal to h, the right hand side goes to 0, and so this gives h dot is equal to 0, which means that the Hamiltonian matrix is diagonal, with the diagonal values being the time independent energies En of the stationary states. Putting f equal to q leads to the Bohr's frequency condition, nu and m equals En minus Em by h. Born, Heisenberg, and Jordan also introduced the concept of canonical transformations, which are transformations from one set of coordinates and momenta to another set of coordinates and momenta, such that the commutation relation between them remains invariant, such that the nu, q, and p satisfy this commutation relation. In doing so, they reduce the problem of solving the equations of motion and finding the energy values to that of solving a matrix eigenvalue problem in linear algebra. Norbert Wiener was an American computer scientist, mathematician, and philosopher. He had studied with Bertrand Russell and G. H. Hardy at Cambridge and with David Hilbert at Göttingen, and was later employed as a professor of mathematics at MIT, where he spent most of his career. In 1924, he gave a talk at Göttingen and met Max Born for the first time, the beginning of another fruitful collaboration between physics and mathematics. In the fall term of 1925-26, Born was invited as a foreign lecturer at MIT and proceeded there soon after completion of his Dreimaler Arbeit. In 1926, Wiener returned to Europe as a Guggenheim scholar, spending most of his time at Göttingen and with Hardy at Cambridge. Born and Wiener introduced operators into quantum theory in their papers, a new formulation of the laws of quantization of periodic and aperiodic phenomena, published in the Journal of Mathematics and Physics of MIT and in the Zeitschrift für Physik in 1926. They defined an operator as follows: an operator is a rule in accordance with which we may obtain from a function x of t another function y of t. Born and Wiener defined the time derivative of an operator A by the operator equation del del t of A minus A del del t equals A dot, and they showed that the energy operator, or Hamiltonian, is identical to h by 2 pi I del del t. They demonstrated the applicability of the new operator mechanics to both periodic and aperiodic phenomena, but it was left to Schrödinger to make the identification of the momentum p with h by 2 pi I del del q. As Born reminisced, we expressed the energy as d by dt and wrote the commutation law for energy and time. It was absolutely the same as for q and p, but we did not see that, and I will never forgive myself, for if we had done this, we would have had the whole wave mechanics from quantum mechanics at once a few months before Schrödinger. Norbert Wiener was famous for his absent-mindedness. As the story goes, once he returned home to find his house empty. Upon inquiring from a girl in the neighborhood, he was told that the family had moved elsewhere earlier that day. He thanked her for the information, and she replied, "It's okay, laddie, Mommy sent me to get you." Asked about the story, Wiener's daughter said, He never forgot who his children were. The rest of it, however, was pretty close to what actually happened.